So far, we have discussed solution of Laplace's equation using Cartesian coordinates and spherical polar coordinates. In this lecture, I want to now discuss solution in cylindrical coordinates. So, we are looking for solution of Laplace's equation in cylindrical coordinates. Again, I will start with a discussion in 2D, and that means I will ignore or not take into consideration variation of potential with phi, and that is we are discussing systems with azimuthal symmetry. Just like we did in the spherical polar coordinate case. So, Laplace's equation in cylindrical coordinates is d2v ds square plus 1 over s dv ds plus 1 over s square d2v over d phi square plus d2v over dz square equals 0, where you recall if we have the reference axis x, then the angle phi is in the xy plane, the angle made from phi. The distance from the origin in the xy plane is s, and z coordinate is like the z coordinate, regular z coordinate. And the potential V is a function of s, phi, and z. For azimuthal symmetry, there is no phi dependence. No phi dependence. Again, taking separation of variables, we write v, s, phi, and z as one function r of s, another function, let's write it capital phi of phi and capital Z of z. And when you substitute this in the Laplace's equation, what you get is 1 over r d2r over ds square plus 1 over r 1 over s dr over ds plus 1 over s square d2 capital phi over d phi square, and you put a 1 over phi also, plus 1 over z d2 z over dz square is equal to 0. So, taking del square v equals 0 and v equals r s capital phi, phi capital Z. Z, we get the equation 1 over r d2r over ds square plus 1 over r 1 over s dr over ds plus 1 over s square d2 phi over d phi square plus d2 capital Z over dz square equals 0. And I can, there is a 1 over z here also and 1 over phi here also. I can now write this as 1 over r d2r ds square plus 1 over r 1 over s dr ds plus 1 over capital Z d2z over dz square equals minus 1 over s square d2 phi over d phi square. There is a capital phi here. Notice that the left hand side is a function of s and z only, and the right hand side is a function of phi only, and therefore this whole thing must be constant. If I take the full range of phi, that means phi varies between 0 and 2 pi, then I have no choice but these functions capital phi have to be periodic, and therefore I should have d2 phi over d phi square 1 over capital phi 1 over s square, and this is with a minus sign, should be equal to some integer m, let's call it m square. Then only I'll have solutions. Let's write this as m square over, okay, I can do better if I write it like this, and I'm not erasing this. I can write s square over r d2r over ds square plus s over r dr over ds plus s over z d2z over has to be s square dz square equals minus 1 over capital phi d2 capital phi over d phi square equals, now it's a constant. Here, what I wrote here, let me write, this was not correct because the right hand side had a s dependence also. And now I take minus 1 over capital phi d2 capital phi over d phi square equals m square, where m is an integer. And this is when full phi range is allowed, because then the solution has to come back to itself as you go around from 0 to 2 pi, and therefore m has to be an integer. So, with minus 1 over capital phi d2 phi over d phi square equals m square, I have phi double prime, where double prime represents the double derivative, plus m square capital phi equals 0, or capital phi equals sine m phi or cosine m phi. So this is one solution for the phi dependence. We'll ignore it when I talk about azimuthally symmetric systems. And then I have 1 over r, that is s square, d2r over ds square, plus s over r, dr over ds, plus s square over capital Z, d2z over dz square equals m square. I'm going to again bring s and z dependence on two sides of an equation, and therefore write this as 1 over r d2r ds square plus 1 over r 1 over s dr over ds minus m square over s square equals minus 1 over z d2 capital Z over dz square. Again, notice that left hand side is a function of s and right hand side is a function of z alone, and therefore this must be constant. Now, there are two possibilities. One is z is a periodic function of z. And the other possibility is z is a hyperbolic function of z. We can consider both cases, but for the time being I am going to consider the second case, and that is I am going to take z as a hyperbolic function, and therefore I am going to take minus 1 over z double prime is equal to minus k square, where k is some constant, and therefore I get z double prime minus k square z equals 0, or the function z as a function of z is equal to either sine hyperbolic kz, cosine hyperbolic kz, or e raised to plus minus k z. Depending on the situation, I will pick up one of these solutions. And therefore, the solution now becomes V s phi z equals some r of s, then I have e raised to plus minus k z, and then I have sine m phi or cosine m phi, this product. Let us now write this whole thing into the r equation, and then you get r equation to be in terms of s d2 r over ds square plus 1 over s dr over ds plus k square minus m square over s square r is equal to 0. Let me divide the whole thing by k to get d2r over d ks square plus 1 over ks dr over d ks plus 1 minus m square over ks square r is equal to 0, and take x equals ks, a dimensionless number, because k is like 1 over L dimension, and you get d2r over dx square plus 1 over x dr over dx plus 1 minus m square over x square r is equal to 0. This is the equation I am going to solve for the r function. So, let us see what the solution is. The final solution is V s phi z is equal to product of three functions. One is this r s, one is e raised to plus minus k z, and this I can write as r of k s, and the third one is e raised to plus minus I m phi. Now, this equation for r is the equation for Bessel functions. And its solutions are the Bessel functions of mth order, which by series solution come out to be x over 2 raised to m summation j minus 1 raised to j over j factorial j plus m factorial x over 2 raised to 2j. And since it is a second order differential equation, there is another independent solution, which is known as the Bessel function of the second kind, nm x, which is jm x cosine nu pi minus j minus mx over sine nu pi, and we take the limit nu going to 0. J minus m x is equal to minus 1 over m, 1 raised to m, j m x. And you can show as nu goes to, nu doesn't go to 0, nu going to m. M is an integer. As nu goes to m, nm and jm are two independent solutions. So, this is the whole thing that we have gotten. We have gotten that if you take this equation in cylindrical coordinates, you get v s phi z as equal to j m x, x being k s, times e raised to plus minus k z times e raised to plus minus I m phi. It's a product of these, and then you sum over m and k. We also look at the other part now. The other case that we had considered and not treated so far was when z function is periodic. So, remember what I had done, I had taken earlier 1 over z d 2 z over d z square to be equal to minus k square, and the solutions we had gotten was z z is e raised to plus or minus k z. Now, we take this k to be positive. So, if I take minus 1 over z, z double prime to be equal to plus k square, then you have z equals e raised to plus minus I k z. So, all you have done is replaced in the equation that k by I k, and therefore, this equation that we had d 2 r over d s square plus 1 over s d r over d s minus m square over s square plus k square r equals 0. I replace that k square by minus k square, and I get d 2 r over d s square plus 1 over s d r over d s plus minus m square over s square minus k square, r equals 0. The solution, and we will discuss them in detail in the next lecture, are the modified Bessel functions. They are given as I m k x, k m k x, or a linear combination of those, and these are related to the regular Bessel functions if you change k to I k. So, we will discuss that later. Now, we will come back to our problem of azimuthal symmetry. So, in this equation, d 2 r over d s square plus 1 over s d r over d s plus k square minus m square over s square r equals 0. If m equals 0, this means azimuthal symmetry. That is, there is no dependence on phi. And we will solve a couple of problems like this. In this case, the R solution K s will be J 0 K s or J 0 x, and the z solution is e raised to plus minus kz, or sine hyperbolic kz, or cosine hyperbolic kz. So, the final solution will be a linear combination of these. Depending on the problem, either k can be discrete or k can be continuous. Since we are using these special functions, I need the orthonormality relations. For J. If you look at these functions, J0 is finite at the s equals 0 or x equals 0, and then it decays. J1 is 0 and then goes like this. Zeros intermingled with the other zeros, and so on. So, there are many zeros of this function at different points, which I am showing by these green dots. I am going to number them, and right now we are considering only the 0th j. So, I am going to call this x1, x2, x3, and so on, or xn is the nth 0 of j0x. Then we have integral j0 xn s over r j0 xm s over r s ds 0 to r equal to r square by 2 j1 xn whole square delta mn. So, orthogonality of Bessel functions is a little different from other functions. The function j0 itself is orthogonal to j0 if the arguments are scaled by its zeros, different zeros. If m and n are the same, then the integral is non-zero and its value is r square by 2 j1 x n square. Let us understand this. So, we are considering integral between 0 and r, and the integral is integral 0 to r s j0 x n s over r j0 x m s over r ds. Let me write this in a slightly different manner, and I will write this as integral 0 to r square root of s j0 x n s over r j0 x m s over r, multiply this also by square root of s. So, these are two functions ds. I am going to plot with black color j0. So, j0 is looking like this, and remember 0 is falling at r. Another j0 may look like, oh, this value is 1 out here, so it may look like this. So, the black one has first, second, third, fourth, fifth 0 here, and the red one has third 0. So, let me use the proper colors. The black one has x5 here, and the red one has x3 here. Let me now multiply both with the square root of s, and both will become like this. As s increases, the value will also increase, but zeros remain at the same point. and the black one becomes like this. So, they are looking like sine functions. With interlaced zeros. So, they had better be orthogonal. Two sine functions with different number of zeros in between are orthogonal. So, that's how you can sort of visualize geometrically how these wave functions are orthogonal. And this is one property we are going to use. So, we have 0 to r, let me write it again, S j 0 x n s over r j 0 x m s over r ds equals r square by 2 j 1 x n whole square delta m n. In case r goes to infinity, then I am going to have 0 to infinity S j 0 k S j 0 k prime S ds equals 1 over k prime delta k minus k prime. In this case, k is a continuous variable. This is fine. So, k is a continuous variable in this case, and this is where it goes to. We are going to use these to solve our problems. So, let us now apply all this to solve a problem of azimuthal symmetry. Problem 1. Given a cylinder of finite height and finite radius, this radius is r, height is h, and the potential is V equals 0 on the bottom surface and on the side surfaces, and it is equal to a constant on the top surface. Find potential V S Z everywhere inside the cylinder. Solution. Now, see, in this case, since V is 0 in the bottom surface, I should have Z dependence such that the function vanishes at Z equals 0, and it is finite at the top surface. After a little thought, you can easily see that the Z function should be sine hyperbolic kz. It satisfies the conditions, and therefore, the solution for V S Z is going to be equal to integral dk j 0 k s sine hyperbolic k z, or summation m j 0 sum k m s sine hyperbolic k m z. Which one will it be? Let us find out. For this, I need the other boundary condition. The second boundary condition is V S equals R Z 0. The side surface is the potential vanishes, and therefore, all Bessel functions must vanish at s equals r, and this implies that kms at s equals r, that is kmd, should be equal to 0 of the Bessel function J0x. So, I am going to have therefore Km equals x m over, this is not r, this is r, x m over r, and therefore, the solution is going to be the summation solution, and V s z is going to be equal to summation m some function a m j x m s over r sine hyperbolic x m over r z. That is my solution. So, for this problem, solution I have is V s z equals summation a m j 0 x m s over r times sine hyperbolic x m over r z. The geometry is like this. The height of the cylinder is d, the radius is r. V is 0 on the sides and at the bottom, and it is V naught at the top. Now, is the last boundary condition that will give me A m's. So, I have V at any s z equals d equals V 0, which should be equal to summation A m j 0 x m s over r sine hyperbolic x m over r d. Now, I will multiply both sides by s j 0 x n s over r and integrate with respect to s to get integral 0 to r v 0 s j 0 x n s over r d s is equal to, the right hand side is going to be summation m a m integral s 0 to r j 0 x m over r s j 0 x n over r s d s times sine hyperbolic x m over r d. Now, I am going to use the orthogonality relationship for this integral and get my values of m. So, let us write this on the next slide. I have integral 0 to r v naught s j 0 x n s over r d s is equal to summation m a m integral 0 to r s j 0 x m over r s j 0 x n over r s d s times sine hyperbolic x m over r d. This integral from the orthogonality relationship is r square over 2 x m square j 1 x m whole square delta m n. And therefore, on the right hand side, I get a n r square over 2 x m square j 1 x m j n x n square should be all x n sine hyperbolic x n over r d. We obtained the right hand side. The left hand side integral is also quite easy. The left hand side integral v 0 comes out, and I have 0 to r s j 0 x n s over r d s. So, to make life easy, let me write this as v naught r square integral 0 to 1 y j 0 x n y dy, where y is s over r. And if you carry out this integral using the series for j 0, which is equal to minus 1 over j factorial j factorial x n y over 2 raised to 2j. You do the integral and you will find that y j 0 x n y dy 0 to 1 comes out to be equal to j 1 x n divided by x n. You substitute this n and you can find the solution, and you will find that v s z comes out to be equal to summation m 2 v 0 over x m sine hyperbolic x m over r d j 1 x m, and on top I have sine hyperbolic x m over r z j 0 x m s over r, and that's your answer. I may have missed a term on top or the bottom, please check it. So, that warning I will give you. Please check for correctness, because while doing it here, I may have taken something on top, something on bottom. So, this is the answer. The second problem I want to do is similar. And that is, if I take a disk in the xy plane, this radius of the disk is r, and it has potential V. Let us say V 0. This is a metallic disk. Of 0 thickness and has potential V 0. Find potential everywhere. So, the solution, what we will do is, again, this is a problem with azimuthal symmetry. So, there is no m, and given this disk, the potential goes to 0 as z tends to infinity, V z goes to 0. Similarly, on the other side, as z tends to minus infinity, V z tends to 0. And therefore, I can easily write that z should be e raised to minus k mod z. And therefore, the solution V S z will be of the form integral 0 to infinity some coefficient a k j 0 k s e raised to minus k mod z dk. And our job is to find a k. Given V S z equals 0 is equal to V 0 for S between 0 and R and S 0 for S greater than R. So, we have now task cut out for us. We have V S z equals integration a k j 0 k s e raised to minus k mod z dk. So, V S z equals 0 is integration a k j 0 k s dk 0 to infinity. We will multiply both sides by j naught k prime s times s and integrate over s. Then we get V 0 integration 0 to r s j naught k prime s ds is equal to integral 0 to infinity dk a k, which I am writing first, integration 0 to infinity s j naught k s j naught k prime s ds. I know this relationship. This is nothing but 1 over k prime delta k minus k prime, and therefore, I get V naught integration 0 to r s j naught k prime s ds is equal to a k prime over k prime, and therefore, a k prime or a k is equal to k V naught integration 0 to r s j naught k s ds, and this integral we have just worked out. This is nothing but k V 0, and this integral we have just figured out is nothing but j 1 k r over k. This k cancels, and therefore, a k comes out to be V naught j 1 k r, and there is an r also. There is an r also here. So, V naught r j 1 k r, and therefore, the potential V S z will come out to be equal to V naught r integral dk j naught k s j 1 k r e raised to minus k mod z. That is your answer. The Bessel integral inside is a little difficult to carry out, but it can be carried out. That is the formal answer. And I will see if I can send you a solution of this integral. Some tables must have it. From this, if you want to find the charge density on the disk, it will be difference of E on the two sides. So, charge density sigma S will be equal to epsilon 0 E at z equals 0 plus minus E at z equals 0 minus, I am writing only E, E will be only in z direction, and this will be equal to epsilon 0 times 2 minus dV dz at z equals 0. And this will come out to be 2 epsilon 0 integral of k j0 ks j1 ks dk 0 to infinity. Again, this integral is a difficult one to carry out, but I am sure some table has it. Maybe these integrals should be looked up in Gretchen and Zick. And the formal solution is completed. So, we have seen how azimuthally symmetric systems can be dealt with in cylindrical coordinates. Let me now conclude this lecture by stating that we developed separation of variables method for solving Laplace's equation in cylindrical coordinates. Then we specialized to systems with azimuthal symmetry and solved a couple of problems. Thank you.